Alright, so today we're going to be talking about the solution of a kth element of two sorted arrays, and we're going to be using the solution to this problem to solve the median of two sorted arrays. So the problem statement is that you're given two sorted arrays, you want to imagine that you've merged them into one big sorted array, and then you want to return the kth smallest element in this array. So for this example, you're given these two arrays, you merge them, it becomes this, and because k is 5, you return the fifth element, which is 6. So this problem is difficult because the way of just merging the arrays and then returning the k minus 1th element is linear in time, and they actually want you to do it in logarithmic time. And so that kind of time complexity constraint makes the problem a lot less straightforward than just going about merging it and returning an element. So let's just dive into the solution. What we first notice is that there's a base case which is really easy to solve. In that case is if, let's say that A, our first array A, had some elements, but B is empty. What would be the answer here? So if you had merged these two arrays, you would just get A, and then you would just return the k minus 1th index here, and so that would be your answer. And of course, it's a similar story. If A was empty and B had elements, you would just return the k minus 1th element in B. So I'm going to write down one array empty implies return k minus 1th index of other. Great. But this is really a special version of the input and kind of not reflected in the general case of the problem. So let's talk about the general case of the problem right now. So what is this general case? So the general case is if we have these two arrays A and B, and they both have values in them. So the way I'm going to explain this is that I'm going to keep along a left index and a right index as well. And then we are also going to consider the medians of these two. And yeah, so the left index I've denoted with L1 and L1 and L2. Right indices I've denoted with R1 and R2, and the middle indices I've denoted with M1 and M2. And so the general idea is that at each step we're going to either get rid of half of the range of A or half of the range of B. And the general idea of the algorithm is that at each step, imagine that we've partitioned the sorted merged array into elements that are in blue and elements that are not in blue. So let's kind of imagine this merged array. We can't actually access it because doing that would be linear, but we can imagine it. So in the best case, all of these blue elements would be kind of contiguous, so that if this length is k, then we can just take the n element. But if we look at the constraints of our input, both arrays are sorted, but there's no promise of any ordering between them. So it can happen that only some of these elements are actually contiguous, and they might be spread across here, right? And kind of the last element here is like max of M1 and M2, or the elements at M1 and M2, so A of M1 and B of M2. But for our thinking, it's good to kind of keep in mind the visual of these guys. being a partition of the merged array like this, even though this might not actually be the picture. And so what we do is, and so from that discussion, we can kind of note that this this length or the amount of elements in here is kind of important. And so I'm going to call it KC. And so how many elements are in this blue partition? Well, that's just M1 minus L1 plus 1 plus M2 minus L2 plus 1. Because there's M1 minus L1 plus 1 elements here, and there's M2 minus L2 plus 1 elements here. Great. So what we want to do is we want to compare KC with K. And then from that comparison, we get two results. It's either less than or equal to K, or it's greater than K. Great. So kind of the general approach that we're going to be taking is that we want to get KC as close to K as possible. So if KC is less than or equal to K, we want to kind of increase KC. If KC is greater than K, we kind of want to decrease KC. Great. And finally, what the kind of the last part of how to break down the problem into subproblems is that we want to compare these values at M1 and M2. So let's just write out the possible results of that comparison. So if A of M1 is less than B of M2 and otherwise. And then we do, we branch out here as well. Great. So if, let's say that KC is less than or equal to K, and then the array of M1 is less than the array of M2. What does this mean? What we can say here is that the answer definitely does not live here. Why? Because KC is less than or equal to K. And we know that M1 is less than M2. So if the answer was less than M1, it either has to live here, live either somewhere here or somewhere here. Wherever A of M1 ends up over here if you do a lower bound or something. But that kind of contradicts that KC is less than or equal to K. So therefore, we're guaranteed answer is not in A from L1 to M1 plus 1 using this Python splicing syntax. And so what we can do is we can kind of break this down into the subproblem. So we can kind of set L1 equal to M1 plus 1. Excuse me, M1 plus 1. And so what we're basically doing here is that we're setting L1 to this, so that next time we run this loop, M1 gets put over here, and then we have kind of more elements in our blue partition. But we also need to keep in mind that we're kind of like discarding these values, but these values kind of still show up at the beginning of our partition over here. So one elegant way to keep track of that and to make sure our subproblem still has the same answer as our original problem is to decrement K by the amount of elements that we're discarding. And so I'm going to write that down right here. So we decrement K by the number of elements that we're discarding, and that the number of elements that we're discarding is equal to M1 minus L1 plus 1. And if KC is less than or equal to K, and B of M2 is less than A of M1, we can just use a asymmetric argument to say that in this case it's guaranteed that the answer is not in, my handwriting is horrible, b from L2 to M2 plus 1. And so what we can do here is we can set L2 to be M2 plus 1, and we decrement k accordingly. Great. Finally, let's say that we're here now, and the number of elements in our partition is greater than k. Then, once we've compared our midpoints, and we found that like we can say something different now. What we can say specifically, so let's say that that M1 compared less than M2. Now what we can say is that the answer definitely does not live here. Why? Because we know that we know that the number of elements in our partition is greater than k, right? So if the element was here, then the element is not in here. But because kc is greater than k, the element has to be in here. And that kind of leads to a contradiction. So, and the reason this works is because we're guaranteed that all of these values are greater than the last blue value in this array, because M2 is, the value at M2 is greater than the value at M1. So I'm going to write this down. So here we are guaranteed answer is not in B from M2 to R2 plus 1. And so now what we do is we kind of update our indices accordingly. So we set R2 equal to M2, this pen is really annoying, M2 minus 1. But here we do not decrement k. And the reason why we don't decrement k is because we are taking away values that are not within our partition. So in this last example, we got rid of values here that corresponded to maybe some values here in the merged array. None of these are blue, so we do not decrement k. And then following a similar argument, we can say that if B of M2 compares less than A of M1, we are guaranteed the answer is not in A from M1 to R1 plus 1. R1, Jesus, sorry guys, R1 plus 1, and so we set R1 to be M1 minus 1, and we don't decrement k. And at this point, that is basically the algorithm. So at each step, if you notice at each step, we're either decreasing the range in A by half, or we're decreasing the range in B by half. And eventually, one of these ranges will go empty, and it'll hit the base case, in which case you can just return the k minus 1 index. And because we're decreasing our search space by half every time, this runs in log A plus log B time. Yeah, so that's the algorithm. Let's implement it real quick. If I can find it. Cool. So this is Geeks for Geeks practice. They have this problem. LeetCode does not have this problem, so I'm using this. And yeah, let's just implement it. So this API, I'm not a big fan of this API. They take in nums1 and nums2 as C-style arrays. So the first thing I'm going to do is to put them in vectors. Plus m. Great. And the way I'm going to implement this algorithm, where every time you kind of change the L's and K's and R's, is that I'm going to implement it recursively. And the way I like to do this in C++, especially since we're doing stuff with indices, is to put it in a recursive lambda. And so the way I like to do that is you bind a lambda to a standard function. So I'm gonna give an alias to this std function type, and the function will take in left, right, k, and return the kth element. And what you can do is you can declare a lambda, bind it to a variable of this std function type, and because the compiler knows exactly what type you want to bind it to, you can now pass this lambda by reference, and you'll be able to call it recursively. So I also want to capture D2 arrays by reference here. L1, R1, L2, R2, E to K. Great. So before I implement this, I just want to write down that we want to return the kth element of 0. So L1 will start at 0, and R1 will go to array1.size -1. L2 will start at 0, and then we'll go to array2.size -1, and then we want to return the kth element here. Great. So now we're implementing this recursive function. There's two cases. There's the base case, and then there's the general case. And let's remind ourselves what those are. So the base case is if either one is empty, you just return the k minus first element. So let's just do that real quick. If my computer loads. Great. So if L1 is greater than R1, and then if L2 is greater than R2. Here you would just return array2, L2 plus k minus 1. And then here it's almost the same thing, but you return array1 at that case. Great. And then in the general case, remember the first thing that we did was we found these middle indices, and then we calculated what kc was. And kc is the number of elements we are storing in this imaginary blue partition. So let's just do that. If this loads, great. And this way of calculating the middle value is so that we don't get hit with integer overflow in C++. And finally, kc is L1 minus M1 plus 1 plus L2 minus M2. Sorry, M2 minus L2 plus 1. This should be M1 minus L1 plus 1. Great. And then finally, we just need to write out these four cases and call the correct subproblem. So we want to compare kc with k. So if kc is less than or equal to k, we want to do something. Otherwise, do something else. And then we want to compare them, the elements at these midpoints. So if a of m1 is less than b of m2, and then otherwise we do something else, and then we can just copy this. Great. So remember that if a of m1 is less than b of m2, we can exclude the values from L1 to M1. So we set M1 to, so we set L1 to be M1 plus 1, and then we keep everything the same, and then we subtract the number of elements we're discarding, which is m1 minus l1 plus 1. And then we could just return that. And then a symmetric argument if b of m2 is less than a of m1. Great. And then let's just go here. So here, remember that if a of m1 is less than b of m2 and kc is greater than k, we know that the answer cannot be from be in the range of m2 to r2. So we just set r2 to be m2 minus 1. And then we do not decrement k because we are not discarding any element which is actually in the partition. And then we do a symmetric argument here. M1 minus 1. Great. And so this is basically the implementation, subject to any bugs that it might have. So just gonna look through it one last time, make sure it looks okay. It might be okay. Yeah, this looks okay. Let's compile and run. Oh yeah, I actually called these array 1 and array 2 and not A and B. Silly me. Let's just fix that real quick. Compile and run. Great, and this gave the correct answer for this test case, so it must work for everything. And it did work for everything. Great. Yeah, so this is how I implemented this algorithm that we talked about for a bit. And yeah, this is implemented recursively. Note that the last thing that happens in every path along this function is the recursive call. So this is a prime candidate for tail recursion optimization in C++. Great, so finally let's just talk about how we can solve this problem, which is the median of two sorted arrays, really easily using our solution to this problem. So this problem is that we are given two sorted arrays. They might not be the same size, and instead of finding the kth smallest number, we just want to return the median of those two sorted arrays. It's basically the same problem, but the one thing that we have to note is that if the merged array has an even size, then what we want to do is there is no one median element. Instead, the median element is the average of the two elements in the middle, which are 2 and 3. So we actually need to find two elements and then add them and take their average. But if the array has an odd size, we could just pick the middle element. So yeah, that's basically the algorithm. And so let's solve it. We can just copy our code here, paste it here. And the first thing I want to do is kind of like make this API take in vectors instead of C-style arrays, since that's much cleaner. These vectors should be passed as constref. And so we can just get rid of these. Everything else can stay the same here, I think. Yeah, great. So let's look at here. Let's find the total size. And then let's also get a handle to half. as well, just for convenience. Great. So we said that if the total size is even, we want to do something, and then if it's odd, we want to do something else. We want to handle these two cases differently. So if the odd case is easier, if it's odd, we just want to return the middle element. In this case, it's the the half plus 1. And if it's even, what we want to do is we want to take the two elements in the middle. So we want to do separate finds, separate kth element calls. So let's just call this, I'm going to call the first one A and the second one B. And then what we want to do is we want to just take the average of them. Yeah, and so this is how you would solve the median two-sort arrays using this kth element solution. And let's just check that it works. Yes, and yes. Cool. Yeah, so that pretty much concludes this video. We looked at the solutions for kth element of two-sorted arrays as well as the median of two-sorted arrays, and we did them both in log of n plus log of m time. Thanks for watching.